Hello everybody, welcome back to Fastware. So due to popular demand, I have finally created a repository. You can find it on GitHub, your Fastware-Rukas, and we have a performance benchmarks repository here. This is all the material that I have covered so far, and we have everything from go-to to university assignment and threading, interview questions and whatnot. So please check it out. And if you have any comments or issues with it, please let me know. Look forward to hearing from you as usual. Now, today we will start our long-awaited series, and all the projects that we'll be kind of implementing and working on we'll be placing into the Fastware repository right next to the performance benchmarks. So if you want to find any code that we worked on, just check it out there. It's all going to be available and public. Usually when the video will be available, so will the code. If it's not, just let me know and I will try to update as soon as possible. Okay? And with that in mind, now let's move and transition to our code. So I already have prepared a kind of a project skeleton of a CMake, which I have a benchmark, the Google test, and the memory folders here. So memory is going to be where we're going to be implementing our custom memory allocators. And of course, you already know that because you saw the thumb on the video. It is going to be the very first project that we're working on. It will be custom memory allocators. I personally love working on it, but you should not be kind of deluded into thinking that it's going to be a replacement for malloc or new. It is not. Malloc and new are general purpose allocators, and this is going to be a domain specific allocator. You can still kind of compose multiple allocators to, in small scopes, behave like a general purpose allocator, but you should not assume that it will replace your new or malloc. Now a little bit about the structure, how I'm going to do this. As I cannot think, write code, and think forward what I need to do at the same time, what I will try to do is speed through a piece of implementation and then slow down. We'll talk about what I've done, and then we will decide what we'll need to do next. We'll go and implement that bit, and then I will talk about it as well. So all the implementation part I will speed through, as there's no need for you to sit looking while I painfully type out characters and implement things. But I will definitely slow down and try to explain every bit how I do it and what I do. Okay? So what I have here is I have the include directory, the perf, the source, and unit directory. So unit directory will be for our unit tests. The perf directory will be for our performance tests. And of course, the include is our header, and here will be our source. I will start with the header and we'll define the API, and then we can move forward from there. So we have implemented a little header, our API. It's not complete yet. Don't get nervous. So quite a few differences from what you would see with malloc or new is we're returning this thing called memblock. It's a memory block describing the address of allocated object and a size, number of bytes allocated. This is quite different from malloc, which just returns a void pointer. The real reason why we're returning size is to inform the callee how much memory there is actually. You might have requested only 10 bytes, but you will get 64, right? If that's the allocator alignment, that's what you're gonna get. And there's a very good reason for it as well. When we deallocate, if you pass the size, we no longer need to shadow and store somewhere that size for this particular allocation. The implementing deallocate functions become much more straightforward, clean, and there's no need for extra code also for allocate functions to hide it. You can still do it, but that's something that I would not recommend to do. Most of the code that you'll be interacting with is more than capable to actually handle the memblock instead of just void pointer. And we have additional utility function for some places where we can't store size in a callee, right? We have a preferred size. So they're exactly the same as you would call allocate with an allocator and the size. We have a preferred size, which is called with the allocator and the size. The only difference is that this just aligns to the allocator's specification and returns the size that it would give you if you would requested that size, right? So how much actual memory it would be allocated. Well, this one actually does the allocation itself. That's the difference. So in the situations where you cannot store the size from memblock on a callee's side, what you can do is basically discard the size, and then when you're deallocating that memory, you just call prefer size on that allocator with the size of the allocation that you used, and therefore we'll be able to acquire the deallocation size that will need to be passed in when you're deallocating the memblock. Now, deallocate all can be useful if you're writing web servers or something that is happening in a loop. So at the beginning of the loop, you start by clearing all your memory by calling deallocate all. Let's say it's very useful for stack allocators. And then you have many allocations that need to happen for different objects. So all of them just allocate on a stack, process, end of the loop, and then return. The same thing for web servers. Begin of request will deallocate all, then allocate resources to be able to prepare the response. Once the response is sent, we can deallocate all. So these are useful tools to be used. Ounce would be primarily implemented when we will have a composition. So you will be able to compose, let's say, a partition, allocator, segregators, and several different types of allocators together, which basically will allow having a parent allocator call, and then it will decide, depending on the size and the alignment of that you requested, which allocator to use and which memory to return. But these are much more complicated things, which we'll dive in much later. There's no need to bother ourselves with that at the moment. So now what I will do is, so as you can see, the create currently takes nothing. What we'll do is start by implementing the stack allocator. We're not going to finish all of it today, but we will definitely start with some utility things, and I will want to show how it's done. So obviously create will be overloaded with different types of allocators that you will be able to create. Today we'll be just starting with a stack allocator. So here we go. Welcome back. So I have done a few small little things. So I created a stack alloc create info t. Given the parent allocator, the size and the alignment, we'll be creating a new allocator. So this will be the stack allocator to be allocated. Now for the alignment, I chose to use this type of a enum structure rather than a UN64 itself. As I'm able, if I have predefined alignments to be used, I'm more capable of actually implementing specific code for each of them rather than guessing what alignment is and trying to enforce that it's, two's complement and it scales properly rather than if it's a free integer input. So that would be my preference to use here. We'll follow up here by implementing few utility functions for aligning our memory appropriately since we have alignment. And we'll start implementing our create, destroy, allocate, deallocate, or preferred size in our CPP file in a second. So let's start with creating few utility functions first. Right. So here we go. We have a little align function and a isAlign function. So align function basically takes a memory address. Let's say it's, 50 bytes. And you need to be 16-bit aligned. So what it does is takes 50 bytes, adds 16, right? That will give you 66. And then takes the OR and negates that mask that you just applied. So removing all the bytes. So that will be producing a 64 byte aligned type, right? Aligned size that will be used for our allocators. Now isAlign uses exactly the same principle, but it just takes memory address, passes to uint ptrt, and then takes that mask and says, does it end with 0 or 1 or 2? If it's 0, it means it's perfectly aligned to that alignment. If there is any remainder, then it is not. Simple as that, right? So what we can do is go there now in CPP and start implementing some of these functions so you can see exactly how at least create is implemented. Let's move there. Okay, so we've done a little work here. So we created an align storage type, which returns a base address of allocation for the allocator and the memory space within the allocator. Then you have a size of that entire space. And then obviously the usable address. A usable address is if you have an allocator aligned to the requested alignment. So from base pointer, if you advance that many bytes, from there you can start your usable address, right? So I think that should be pretty clear, right? And usable size is obviously, so both usable address is subset of base address and usable size is obviously a subset of size. So when you're creating, you want the allocator size, as I said, because you will need to do that adjustment to figure out where usability address starts. You have memory space size, so how much bytes do you actually need for this allocator, and what is the alignment for that allocator. So these are pretty straightforward bits, I believe. Now we'll be implementing the create aligned storage later on, which probably will utilize the aligned alloc from the standard library and our own allocate function if parent exists, and exactly the same thing for destroy, which will be free or deallocate if the parent exists. So I will upload this code to the repository so you can guys check it out, look at it, scrutinize it, maybe implement other functions yourselves if you feel up to it, of course. And then I'll see you in the next video where we'll be continuing this implementation. So as always, if you enjoyed it, please leave a like and subscribe to the channel if you want to support me. And have fun writing fast code. Cheers. Bye.